properties and chemistry of amines. And I hope you notice as we work our way through this that we have done a lot of this. There is very little new chemistry from now on to the end of the term. When we come back on Monday and we crack into the latter chapters, which I condense, you'll see that a lot of the stuff we've covered. It's just putting it together with bigger molecules. And I'm writing the final, and the final is, again, an attempt to make sure that you understand what's going on. You just can't memorize this stuff. You have to show that you've learned something. You have to be able to look at new problems that you haven't seen before and have a go at them. Now, in terms of where I'm at, I'm talking about nitrogen, I'm talking about amines, and again, we've done enamines, we've done imines, so a lot of this is just review. These things are nucleophilic. These things are basic. They have a lone pair. They are more nucleophilic and more basic than oxygen in, for example, alcohols, because nitrogen is less electronegative and it can give away its lone pair easier. But there are some interesting properties with nitrogen that you don't get with nitrogen that you do get with carbon, for example. And you can see here the shape of this thing is approximately tetrahedral, which you would expect because you've got four things, which includes the lone pair. Don't forget the lone pair is a valence. So this thing is approximately tetrahedral. We'll say it's sp3. We built that picture a while back, all the way at the beginning of the two terms. And we can see now if we think about chirality, you might expect these things to be racemic. You might expect these things to have chiral centers. And the idea is they don't, and that's because of this idea of pyramidal inversion, in which that lone pair can actually change its position. Okay, it's like an umbrella blowing in the wind and inverting. And you can see now that the barrier for this isn't very high, about 25 kilojoules per mole. That's not a lot. So you get this inversion process that's happening all the time with these amines. There are some examples where you can trap an amine as a chiral center, but not very often, right? That's sort of a graduate level idea. But as far as you're concerned, these things are not chiral. Even if you do have four different things attached, they are not chiral centers. So be aware of that, that they're a bit more simple than alkanes. Now, physical properties, just to get this out of the way, and then we'll talk about some reactions today and get this thing finished. Colligative properties, basically this idea of boiling points and things like that, what pressures or what sort of interactions are occurring between molecules to affect the outcome in terms of a boiling point or a melting point. You can see here molecules that are very similar in terms of their molecular weight and their molecular size. But the difference here in their boiling points is quite dramatic. And don't forget, as you move on from organic chemistry, you'll find that in biochemistry, obviously, the temperature range isn't very much. If it is, you're in trouble in terms of how biochemistry works. For organic chemists, it's negative 100 to plus 200 is really the playing field. So in this system here, where we've got negative 42 up to plus 78, that's a vast difference for those molecules having very similar molecular weights. And the answers are fairly straightforward. Typical MCAT, PCAT type questions that you see all the time. Why is this so low boiling? Why is this a gas at room temperature? Very few intermolecular forces holding things together in terms of breaking those molecules apart. Not smashing the molecule up, but breaking them away from each other. And so that's a very low boiling material. You move up to this guy, this one has a lone pair, and it has some protons which are delta positive, so you can actually infer here that you'll get some hydrogen bonding, and the boiling point here is 17 degrees C. So that's a gas at room temperature. And then you move up to alcohol, to ethanol, and you've got more possibility. You've got two lone pairs, you've got a bigger dipole between the O and the H, and so the hydrogen bonding is more significant, and you get up to 78. So those things should be fairly straightforward in terms of applying those if you see them in the future. Amines within the series, you can see here it's a similar thing. If you start taking off the hydrogens, the boiling points go down. Obviously, if you don't have any hydrogens, you can't have any hydrogen bonding. So on the left, you've got 50 degrees C for propylamine, two hydrogens, lone pair. You can certainly do hydrogen bonding there. Likewise here, but not as much for ethylmethylamine. And then trimethylamine down here, no hydrogens, no hydrogen bonding. So the boiling point goes way down. Simple things that I think you've taken on board, and I hope we can see that on the final. Now, some of my favorite amines. Guess what these things smell like? Amines in general are nasty, right? You know amines are around when they're around. You will see cadaverine in the future, I would imagine, in biochem, and you might well see putrescine. Putrescine, they stink, right? Triethylamine stinks. And these molecules are breakdown compounds for molecular catabolism in terms of breaking down molecules, so you'll see these in the future, and you'll recognize that they are simple amines as we would see them as organic chemists. Things that we've seen in the past, because we've already done this, so let's fly through it. Pyridine, weak base, good solvent, nice for acylation reactions with acid chlorides, things like that. Triethylamine, likewise. Triethylamine was used in the trimethylsilylation of alcohols way back when you made the TMS derivative as a protecting group. So these things are moderate bases. They're not going to rip a proton off a substrate, but they will mop up a proton after something's happened. These are very good sort of proton sponges, you might say. In terms of reactions, we've seen acids and bases. We've seen a lot of this stuff. Go back and look at this again. the idea of pKa, the idea of understanding those numbers, take it with you because you'll see it in biochemistry again in the future, and more than likely physical chemistry. And you'll see here now that bases, amines are fairly basic. They're not strong bases, but they can deprotonate things like carboxylic acids with low pKa's. And we end up on the right-hand side. And what you want to take home from today is the idea that the conjugate acid of an amine has its own pKa, and it's typically in the 10 region. So that's like a phenol, right? So it is somewhat acidic, but not as acidic as others. And those acid-base reactions you should be able to balance for now. We should be able to talk about why basicity decreases in certain instances. If you put an electron withdrawing group next to a lone pair, that lone pair is less basic because the lone pair is delocalized into the system. And you'll see that in the next couple of slides where we start to talk about anilines. And you can do a series here where you put different groups on the benzene ring, and you see the basicity fluctuates. It changes based on what that group is. So here we can see now that from benzene chemistry, there's a lot of benzene chemistry on this test, so go remember it. You can see here the lone pair is delocalized into the cycle. So if you had a cyclohexylamine with no pi bonds, it would be fairly basic. If you have the aniline like this, it would be less basic because the lone pair is busy delocalizing. And we've all seen these resonance structures before, and we should be happy with what they mean and what they tell you. So these anilines are not as basic as the simple amines. And that shows in these charts. These are just some examples to show you how consistent this is. If you have a simple aliphatic amine, in other words, no pi bonds, no benzene rings or anything like that, the basicity is roughly the same. As you work your way down from methylamine down to cyclohexylamine, the basicity is the same as measured by the conjugate acid strength. You can see 10.6 and 10.7. That tells you the base strengths are roughly equal. So nothing here in terms of delocalization on the left. Similar on the right, no delocalization, so the pK of the conjugate acid is about the same, telling you that the base strength is about the same, as would make sense. And the whole point of what we've done so far, I think in this 2 semesters, is to learn that R groups are important. So the R group, the idea of putting something generic on here, really matters, because as an organic chemist, you can say with confidence that the basicity of this thing up here is the same as the basicity of this thing down here, even though the structures are quite different. You've learned that. You've learned what's good in a molecule, what's reactive in a molecule, and what isn't. So we're happy with that, hopefully. Now, this is the opposite. These are examples that we've seen before where the basicity goes down because the lone pair is busy doing something else. You can't give it away if it's stuck in a pi system, for example. Here, 4.6 is the pK of this, telling you this lone pair is less basic, and the answer is because it's delocalized. You can see down here, similarly, for putting a couple of methyl groups on there, doesn't make much of a difference. You end up with roughly the same pK of the conjugate acid. Now, on the right-hand side, we've got some systems that we have seen before. This is a very low pKa, 0.4, 0.4. Any ideas why this is so, why is it such a weak base? This is a fairly strong acid. Why is that such a weak base? That's exactly right. The lone pair is part of a pi system that is aromatic. You take that lone pair and you use it as a base, you lose the aromaticity. So therefore, that's unfavorable. So that tells you that this material over here on the right, the conjugate acid, wants to give up that proton and go back to being the base. That's why it's a strong acid. So remember those little details. They will be important soon. Pyridine down here, a little bit opposite. We compared these two a while back when we did the aromatic systems. You can see here the pyrrole, the lone pair is part of the pi system. The pyridine, it's not. In pyridine, you already have 6 electrons in that cycle. You don't need the lone pair. So the lone pair is sticking out and can be used as a base. That's why it's more basic. So common sense, simple, straightforward things. This slide, nothing more intimidating than a series of compounds in which we change the R group on a benzene ring. And you can see here that the pKa's do change dramatically. We go from 6.2 at the top for the conjugate acid down to 1.0. And what's changing? What type of groups are these at the top? What type of group is NH2, OMe, Me? Activating or electron donating. And as you work your way down through the 0 point where you've got the hydrogen there, and you end up with the deactivating substituents, which are electron withdrawing, you find now that the material has become less basic. And I want you to be okay with that. When you head into biochem, you'll need that sort of idea. Why is the lone pair in this less basic than all the others above it? Okay, so the nitro group is super electron withdrawing, and it's pulling that lone pair towards itself, therefore it's not available for being a base, or not as available as materials above it. So it's a simple idea using benzene chemistry to sort of talk about acids and bases in this idea. And again, you'll see examples like this beyond my class. You'll see anilines, and you'll see amides at the bottom, stuff like that. If you can delocalize a lone pair, it will be less basic. And if you can delocalize this lone pair on the end down here in the amide, it will be less basic again. And amides pretty much are not basic at the nitrogen. You'll see that in the future. So fairly simple things. We are going to prepare amines, and we've used them already. So a lot of this stuff will be cyclical in the sense that we've already done it. We can do simple amine chemistry as follows. We can take alkyl halides all the way back from the first term. We can add a nucleophile, such as sodium cyanide, and do SN2 chemistry. Knock out that bromide, extend the chain by 1 carbon, And then we do this. Now, we're not going to spend a lot of time on this mechanism because I would hope people can get it from now on. What is LAH? What does it serve as? H minus. Is it weak or strong? Strong, right? And it says excess. So what do you reckon excess tells you? It goes again. Yeah, it reacts once, then it goes again. So you can imagine now H minus is looking at this molecule. And where is delta positive in that system? Carbon. Right? So H minus goes after carbon, 2 electrons up onto the N. Right? Do it again, and then we end up with this reduced form. So it's a nice way of making amines by introducing the nitrile, which we can do by simple SN2 chemistry, and then away we go. We've also done it this way in the previous chapters when we talked about carboxylic acid derivatives. You can see here, start out with the carboxylic acid, mix it with SOCl2, react it with an amine, you get an amide. That should be in there by now. In this reaction, again, look at the similarity between this one and the one at the top that we just talked about. LAH, strong nucleophile, H minus, goes after the carbonyl, just like it did up here after the carbon up there. And you do this twice. And again, you've got to be careful here because the O serves as the leaving group, not the N. This is different. We talked about that a while back. And we can see here now that we introduced 2 hydrogens and we've lost the carbonyl. Or at least we've lost the oxygen from the carbonyl. So these are things we've done. Down at the bottom, familiar chemistry. Go back and look at your ortho-para-meta stuff, or the idea of activating, deactivating substituents for the final. Nitration using nitric acid, sulfuric acid, which I think you've done yourselves. Put a nitro group on, and then you can get rid of it by reduction. And all of these conditions work. I prefer at the bottom the tin chloride, and then at the top you can do hydrogen platinum, and again that will just give you the NH2 group. So it's fairly simple. Now, why doesn't the benzene ring go? I'm using H2. Why doesn't all of this double bond system go? Stable. Yep, it's very stable. You want it back, so don't get rid of it there. In terms of making amines from scratch, this is an interesting problem. And I would think that people can get this now, having understood Friedel-Crafts chemistry and having understood, for example, reduction of esters, which go all the way down to primary alcohol. In some of these reactions, you have produced products which are more reactive than what you started with. And that was always a problem, for example, in over-alkylation during the Friedel-Crafts reactions. You over-alkylated because the product was more reactive than the starter material. And you got a competition between the product and the starter material for whatever reagent was left. And this will happen the same here. So it'd be very handy for us as chemists if we could just take ammonia, because there's a lot of ammonia around, and we can alkylate things. If you just simply alkylate ammonia, you might be able to produce a primary amine. Nice, cheap way of doing it. Unfortunately, it's rubbish. It doesn't work. And the reason it doesn't work is because the primary amine is more reactive than what you start with. Any comments? Why should having a methyl group here make this more nucleophilic than what we started with? Electron donating. We're having some good thoughts now. You can see here the sequence is fairly straightforward, and it combines SN2 and acid-base chemistry. You can see now the amine is behaving as both. In the first reaction, the ammonia comes in as a nucleophile, does an SN2, kicks out the leaving group, and you form this salt. Now, the chemistry might be such that you set it up so the salt precipitates, maybe, from the reaction. You can isolate it that way. Or, if you're in solution still, a second equivalent to the nitrogen starter material comes in and deprotonates to give you ultimately the primary amine. But the problem is this material at the far right is more reactive than what we start with because this methyl group is pushing electrons into the nitrogen, making the nitrogen want to give that lone pair away. So it's more nucleophilic now. So what we'll find out is that this reaction isn't much use other than going all the way to the quaternary salt, which is the thing at the bottom. So the first example, ammonia, primary amine. Go after this, do an SN2, form the primary amine. That involves a deprotonation step. Second reaction goes again because the product is more reactive than where we started. Then we can get to a secondary amine after a second deprotonation. Then what we can do is go again with a tertiary amine and carry this on all the way until you form these things. Now these things have a lot of use. They are very useful as detergents. Look on the back of your shampoo bottle next time you take a shower, if you do, and you will find these things are in there. Quaternary ammonium salts help solubilize material. So that's what this is useful for. You can't really stop at any of these intermediate products because they keep going. And you get these mixtures and you want to make it worthwhile. So just like we did for reducing esters, where we said, all right, one equivalent of LAH doesn't work because it goes to the aldehyde and then it goes again and then you get some starter material left, you just add more reagent to make it go all the way. So you would say here, ammonia plus excess of this will allow you to go all the way to the quaternary salt, and that's what this thing is at the bottom. So with that in mind, we're just finishing some things up. We're talking about amine syntheses, so we can actually use them now. We can go back to simple materials and then build up enamines and things like that. I've got here the azide synthesis. This is one we like a lot, something that we've been working on in my lab for a while. You start out with some leaving group on an alkyl group, and you bring in sodium azide. The problem with sodium azide is if you hit it with a hammer, it goes bang, right? It explodes. And this is one of the bases of airbags. It was used in airbags for years. And it's a bit toxic, and it forms HN3, which is poisonous, so people want to avoid it. You do an SN2 reaction with sodium azide. Would anybody like to give me a good solvent for this? If anybody was to come into an organic lab and try to set this thing up as a research student, which some of you want to do, what type of solvent would you use for this reaction? Polymerase protease. Do we have any examples? DMF, DMSO, things like that. That will work nicely. And that will give you solubilization of all the material, and that gives you the product. Now, again, mechanistically, I'm not so concerned about this. I'm not that bothered about whether you understand this mechanism at the bottom or not. It does involve evolution of nitrogen gas, and I'm not going to test you on that. That's a mechanism that we're not that bothered about. We can reduce these things with the same type of conditions we did previously. We can take out the nitrogen by adding a hydrogen. Notice N3 goes to NH2, and then we can use LAH likewise, and that will bring in the H2. Simple methods to get to amines. Keep this in context. This final now is a test of everything you've done since you ever heard the word chemistry. Right? And hopefully that was about 4 years ago, maybe 5 years ago. And you've got to understand now that reductions are important, oxidations are important. You've got to be able to identify them. I'm seeing people struggle with that at the moment. And you've got to be able to do functional group manipulation. You can start all the way back at carbon now, or alkanes, and you can go to alcohols or bromides, and you can turn them into azides, turn them into amines, turn the amines into enamines, turn the enamines into beta keto whatever by doing aldol type chemistry, and we've gone a long way. So some examples here how to do this. You've got to be careful. You've got to watch out for carbon counting. Make sure that you've got the right number of carbons in a molecule, or else it gets all messy. At the top I have an example of a simple azide reduction in which we take hydrogen, palladium, and we reduce this down to the NH2. And the point of this slide is that you don't get any extra carbons in the product. You're not introducing any extra carbons. So here we can see at the bottom, if you use the cyanide material, you have introduced a second carbon, or an extra carbon. So that's extended the carbon chain by 1, and if you then reduce that down, you get a longer chain, which includes the C and the N. But both are very simple ways of going to amines. Well, the best of the lot, to get around these problems of over-alkylation, is to discuss probably the reaction in this chapter. Okay? The one that comes up next is a combination of two that we've already seen. This one is a little bit unique. And it's called the Gabriel amine synthesis, after the person who invented it. And what you start off with is this material here. And this is kind of fun because it's very cheap, it's solid, it's easy to work with, and it allows you to get clean and very high yields of primary amines by doing some very simple chemistry. And we have covered every single step of this. I have an example of it here from the website, but we've covered all this stuff in its individual components. We just have to now put it together. So in the first step, look at what happened here. KOH reacted with NH to give NK. What type of reaction is that? That's an acid-base reaction. So why should this proton be acidic? What is the normal pK of an NH bond? 38. Now this is nowhere near 38. It's much, much lower. Why? Yep. You've got two flanking carbonyls, which are going to delocalize any negative charge. So this proton is considerably more acidic. Down there, the pK is 8.3. That's a dramatic difference. Take this proton off, and you end up with this. Now, this is a salt, and the nitrogen is negative. So the nitrogen here is nucleophilic. And if you put this in the presence of an alkyl halide, you will go after that alkyl halide and kick out the bromide. What mechanism will that be? SN2, that's all it is. And you produce this N-alkylated species. And that's the end of that process. You can see now that we're stuck at that situation because we don't have any more protons to take off. We can't put any more alkyl groups on. So it's a nice clean reaction that stops there. What we do next is liberate the amine. And this mechanism is a lot more straightforward than people make it out. You take hydrazine, and we've seen that before with the Wolff-Kishner reduction. It's rocket fuel. It's a very useful molecule, and it wants to react. So we'll find now that this material here reacts with this dicarbonyl system to kick out the NH2. And I have an abbreviation for the mechanism on the next slide, and we'll maybe talk about this more in recitation. But I'm not that interested in this stuff, right? It's a nice compound, nothing against it personally, but I want this. That's my primary amine that I'm after. And you can see a very, very high yield through some fairly simple, cheap chemistry. In terms of mechanistic ideas, here's from my website, and I want to point this out as what I tried to do to put this on one slide, but I want you to do the whole thing if I ask you for the whole thing. We can see here in the first step, acid-base chemistry between the KOH and the NH bond. Form a nucleophile. That nucleophile down here is nucleophilic, obviously, goes after the alkyl halide after you add it. You do an SN2, and you end up with the N-alkylated material. Now, this has got to be careful here because these little dashed arrows are my attempt on the internet to put this on something that's useful and doesn't become unwieldy. But you can't do that. All right? That's illegal. I got my graduate students out of this bad habit. What they want to do for a nucleophilic acyl substitution is attack, push electrons up, push electrons back down, and have a leaving group break off, all at one go. It is a stepwise process. You go through a nucleophilic acyl substitution process. You form a tetrahedral intermediate, which then collapses. If you want to have hydrogen transfers, proton transfers, do so. But I want to see all the steps. And again, likewise, notice what's happened now. We've introduced this N to the one side of the molecule, and we now have the second lone pair, and we have a carbonyl very close by. So as you've seen with the Robinson annulation and things like that, when you have more than one functional group in a system, it can cyclize if the right conditions are met. In this example, we have a nucleophile at the bottom, which is now tied to the system, and I can see here attack at the carbonyl should be favorable, and that's how we get to these two products. Have a look at that. If you're not happy with it, ask. So we can use this in design. We can put this together to actually come up with a synthesis if we want the product, and we can design our outcome. And this is an example of a synthesis of amphetamine. Okay, this is just an example. Now, the problem with amphetamine is it's a chiral molecule, so here you're going to get a racemic mixture. But in this case, we're trying to make it. So how do we make it? We recognize that the N part of this material came from the starter material down here. And the name of this starter material is phthalimide. Right? Phthalimide. And again, the sequence here is just showing you what you can do with this, but the point is that you can design this now. You know that the nitrogen comes from the phthalimide. So all you need to come up with next is the alkyl component. If you can make the alkyl bromide, you can do this reaction. And you can go from a very simple starter material like this to the complex biological product. So you can use that in synthesis. There are some synthesis problems on the final. Again, if you're not happy with that, come and ask, and we can practice. Last thing in this chapter, really, there's some bits and bobs at the end, but the chemistry here really finishes with this. The idea of using amines to couple things together. You think about what we did with esters and ethers and things like that. Remember, go back to ethers. Ethers were carbon, oxygen, carbon. And you can make them from alcohols by taking carbon, oxygen, and attacking another carbon. You can take this big carbon piece and this carbon piece and stick them together. So the ether is like glue holding those two things together. You can do the same things with, for example, esters. You take one piece, which is a carboxylic acid, you take the other piece, which is an alcohol, and whatever those carbons are attached to them, come along with those two pieces and you form an ester. And you link them together. Now in biology and biochemistry, it's been developed that some of these linkages are very robust. They don't break down very easily, like ethers, or some of them are labile. They last temporarily until they're finished, such as esters, such as amides, and in this case, sometimes imines. So I've said in the past that amines are, I think, much more versatile compounds than alcohols, because the alcohol only has 2 valences, whereas the amine has 3 valences. And if you start thinking about linking things together, you can imagine taking a ketone, some amine here, and forming an imine. Now, if this H is replaced by R, and R can be huge, right? It can be something very important like a protein. You have a linkage between this piece here and this piece here. And imines are useful because we know it's temporary. You can go back to a ketone. What do you take to go from an imine back to a ketone? What chemistry do you need? That's it. Acid catalyst and water will take it all the way back to the carbonyl. So that's a temporary. That's like a switch. You can go on and off, attaching these things backwards and forwards. Well, if we now think about how to make this a more robust linkage, making it more permanent maybe, we need to get rid of that carbonyl, because that's the thing that's getting hydrolyzed. So maybe we can reduce that. Maybe we can bring in sodium borohydride and methanol, or we can bring in hydrogen palladium, something like that, and we can reduce this down, because these things are not great leaving groups, and these things are not going to be broken down very easily, whereas the imines are. So you can see later on with functional groups in biochem that the choice of these things is very useful in terms of different jobs that need to be done. Now at the bottom I got 2 reagents, one of which you've seen, one of which you haven't. Sodium borohydride right here is something you've seen before. A modified version of that is sodium cyanoborohydride. And that cyanoborohydride, the CN group there, makes a little bit of a difference. What do you reckon this is? Electron withdrawing or electron donating? Withdrawing. So if all the negative charge in this molecule is built upon the hydrogens, making it reactive, what do you think the cyanide does? Does it make it more stable or less stable? It makes it more stable, right? It makes the system a little bit less reactive because it's helping the charge spread out a bit. So this actually is a fairly mild reducing agent. It's milder than borohydride. And you think about that now, you have sort of a hierarchy. LAH is the nuclear option. It'll reduce pretty much everything. Sodium borohydride can be used for selectivity. Sodium cyanoborohydride, even more so. And it turns out in reality, there are dozens and dozens of these reagents that you can pick and choose off the shelf to do what you need to do. And that have been developed over the years. So we're going to do something called reductive amination. Let me point this out. Reduction, obviously at the end. Amination, you're making an amine. You need a ketone or an aldehyde, an amine, and some reducing agent. This is one of the most useful pieces of chemistry in pharmaceutical chemistry to be able to introduce nitrogens and to be able to reduce things down and produce amines. So in terms of how this works, keep an eye on the starting materials, keep an eye on what you are trying to do here. It's nothing more fancy than forming an imine first, which we can do, and then reducing that imine as we have done in the past. But this guy down here it's a subtle nucleophile. And the answer is fairly simple. At this stage, it probably isn't the imine that's getting reduced. It's probably the protonated version. So that's an iminium salt, and that's actually more electrophilic than what we start with. So this cyanoborohydride material here selects this because it's more reactive. If you use LAH, just scorched earth, everything dies. So this is going to make it much, much easier, much better. Now, to finish this, we are looking at different examples. We have ammonia in the presence of acid and sodium borohydride, and it gives you very nicely the primary amine. Don't get lost on amine nomenclature. That's a secondary carbon, but because at the end, the nomenclature is a little bit different. If you have one carbon group attached, it's primary. And it's very clean, very high yielding. Down here, same conditions other than changing this to a primary amine. Going through the imine, you get this, which is a secondary amine, and you can go all the way down here to a tertiary amine. It's a very, very versatile, very, very well understood reaction. Okay, here's an example in biological chemistry, how to use this stuff, how to design. Fluoxetine, I don't know what fluoxetine is. Any pharmacy type people out there? What's fluoxetine? What? Antidepressant, okay. This is built by doing exactly what we just talked about, built by doing reductive amination. So in this molecule, there needs to be a coupling at the end over here, and you'll see now that that's where the retrosynthesis is involved, and you can take this thing apart and you can turn it into an aldehyde and turn it into methylamine. So methylamine is going to be a nucleophile, it's going to form the imine, and the imine is going to get reduced, and that's going to give you that product. That's just an example. It's very straightforward. Look at it for 5 minutes and it'll be fine. Okay. In terms of the design here, this is an argument about precursors. Again, your synthesis might be different to somebody else's synthesis, and sometimes your synthesis is better than my synthesis, something I didn't see, which is always fun to see at the end because people really are starting to get this stuff. The argument on this slide is that you can do this in two different ways. You can start off with an aldehyde or you can start off with the amine. It depends what you have, it depends what nature gave you. If nature gave you a ton of this stuff, use this. If it gave you milligrams of this stuff, don't use this. And that's something that you might not know, but will sort of become more apparent as you progress through the latter classes. And they're both fine. They both work the same way. You can use the same chemistry, and you get the same outcome to form that fluoxetine. So the point is, it's very important, very useful. You have some very useful ways of making amines. How important are amines? Incredibly important. You can do the Gabriel amine synthesis, starting off with the salt of the phthalimide, and do an SN2 reaction followed by hydrolysis, or you can use NH2 here, and that gives you the primary amine. Azides, likewise, you can start off with N3-, do SN2 chemistry, reduce, you get the amine. And then also here, simple example, reductive amination, start out with some amine, make an imine, reduce it, you're at the amine. Not much to this. In terms of making more elaborate outcomes, we said that this is not a very good process if you simply mix an alkyl halide with ammonia, because it just keeps going and going. This now is useful because you can control things. If you're doing the primary amine synthesis, starting off with the primary amine, doing a reductive amination, you can simply make a secondary amine, and it can stop there. If you want to go further, you can use this to make an imine, and then you can go further again with reduction, and you can make a tertiary amine. So you can design what you want, and you can select what you want in terms of outcomes. They're very useful, very high-yielding reactions. At the end of this, you really can't do a reductive amination with this, okay? But you can certainly use those molecules as nucleophiles, and you can go further to what's called a quaternary ammonium salt. And again, those compounds are probably things you've dealt with in the past. This slide is just showing you the summary of all that stuff. Put it all together. SN2 chemistry, reductions, nothing too tricky there. I would be looking at that slide as a summary, making sure that you're okay with the different components. Now, amines themselves, we have seen a whole bunch of different reactions in which they are nucleophilic. And we can use these things to go further and do further reactions and build bigger molecules. At the top, we have done this. We have taken primary amines, secondary amines, what have you, treated them with acid chlorides, and we have turned them into amides. Technically, you don't need an extra base here. Technically, what you would do is maybe add 2 equivalents of this material to get this to work. You still need to get rid of the HCl at the end, but if you have the amine in there, it's already basic. It can do the mopping up for you. You don't need the pyridine in there as well. So you might see this with an excess of the amine plus an acid chloride gives the amide, And for those of you going into polymer chemistry, biochemistry, amides are going to be incredibly important. That's a nice way to make them in the lab. Down at the bottom, why don't I need a catalyst down here? It says right there, doesn't it? It's strongly activated. Why is it strongly activated compared to other molecules? What does nitrogen have at the outside here that allows this to be activated? A lone pair. That lone pair pushes in, and just like the methoxy derivative that we talked about, the anisole, this is going to do bromination again and again without a catalyst because it's that nucleophilic. Even though that lone pair is part of the pi system, in this case that helps by making the benzene ring more nucleophilic. So you don't necessarily need to have a catalyst right there. Well, we can use this amide as a group to help tame the NH2 group. What's happening here? What is this group behaving as in effect? Blocking something, isn't it? It's kind of blocking something. So you could think of this as being a protecting group. And what you start out with is aniline. And the problem with this is that it's also reactive at the nitrogen. And you can get an acylation reaction where you make the amide. And so acetamide here is going to be more reactive or less reactive? Well, it says down there less nucleophilic. Why is it less nucleophilic than where we started? Exactly. Delocalization of the lone pair from the N into the carbonyl system really tames the reactivity of that benzene ring. So now we can get, in this case, monobromination. In the previous slide, it went all the way to the tribromide. You couldn't stop it. Here, you can selectively get one bromide because you've tamed and calmed down the reactivity of this species at the top, and then we can get rid of it. Now, this isn't particularly straightforward chemistry. Sodium hydroxide, you probably have to heat these things up because that amide is fairly stable, and to liberate this requires a bit of a kick. But you can get rid of it, and now you've selectively got something like this very useful. The last thing, really, in this chapter is an alternative to Zaitsev elimination. What was the point? What was the background to Zaitsev? What type of alkene did you always get in Zaitsev eliminations? The more highly substituted. Now, what happens if you want the less highly substituted? Yep, you have to use a sterically hindered base such as what? Potassium T-butoxide, POTBU. All right, everybody's favorite. You could use that if you want to. But this has been developed, this Hofmann elimination, as an alternative to that, using amines. And contextually, going back to the stuff that we started with here, with Woodward and Robinson and people like that, trying to develop this chemistry from scratch, they didn't have some of those reagents. They didn't have the same technology that maybe we have now. And this was useful because this is a way of getting nitrogen out of your molecule, leaving an alkene. And a lot of their chemistry was nitrogen-based. So we've done in the past elimination reactions where we take an alcohol and we put a double bond in there. You might think about protonating this thing and heating it up, or you might put a tosyl group on there and put some base in, and it does elimination chemistry and it gets right here. Or you might think that taking an amine might be useful because guess what? Amines are the nitrogen equivalent of alcohol. So why don't they work the same? Well, they do. We can eliminate this thing and we get the alkene. But regiochemically, it's a little bit different. It's the opposite of Zaitsev. Well, to do this, we need to turn this into a leaving group. And this falls into very similar ideas that we've dealt with. You make the leaving group positive, it breaks off. So you do this in this case by adding alkyl groups. You make this a positive nitrogen and it can break off. But it will happen only in the presence of base. So this Hofmann elimination is the opposite of Zaitsev, and it looks like this. You take an amine. You alkylate it with an excess of the alkylating agent. And then you treat that species with a silver salt, and you heat it up in water, and you get this outcome. And the outcome on the right there is the opposite of Zaitsev. This is the Hofmann outcome. So what do? We alkylate this thing continually. Why do we need an excess? For the same reason we did that just previously. It doesn't alkylate cleanly. It goes again and again. Well, we can use that here. Alkylate this material at nitrogen to give you the quaternary ammonium salt, where there are 4 carbon groups attached onto the nitrogen. Then add some silver. Any idea what silver does? Go all the way back to freshman chemistry. What does silver salt do? What does Ag plus do? Look what's in there as well. What does Ag plus go after? Iodine. Silver has this ridiculous attraction to iodides and fluoride and basically halide salts. So what will happen here is we will sequester this iodide with the silver, get rid of it, that might well be a precipitate, and you swap the anion here for hydroxide. And what can hydroxide behave as? A base, absolutely a base. So we now are set up to do an elimination. We have the base, we have the potential leaving group, we have the substrate. The question is, why on earth does it go in that direction and not do Zaitsev elimination? Well, a lot of this stuff is down to conformations. It's down to the fact that this group right here is quite large. So when you look at this as a Newman depiction, maybe that can only be in certain places. Maybe it doesn't want to be overlapping with other things. Maybe it doesn't want to be gauche to other things. So this E2 here allows for formation in high yield of the opposite product as Zaitsev. You get the lesser substituted alkene. Not because the alkene is that much more stable, it isn't. It's always the more substituted that's more stable. It's to do with the transition state to get to that product. So look at this. If you look down here, as this little diagram is trying to show you, look down that picture. In this example, you've got a problem. If you set this up to do the elimination to give the Zaitsev product, these two are going to get in each other's way. That's a problem. So what do? You rotate. The molecule prefers to be in this conformation, where the two alkyl groups, or the two big groups, are away from each other. What that then leads to is the opposite proton being preferred. We now prefer a proton on the methyl group at the other end, not inside, not an internal proton, and we can now get the external alkene. So have a look at that. It's simple stuff in the first term. That's a problem. Why is it a problem? Gauche? Don't want that. Rotate a little bit. Set this up. What is the relationship between the leaving group and the proton? Anti, right? An anti-periplanar, which is necessary for a fast E2. So this allows for that at the end of the chain, and that gives you the Hofmann alkene. So again, what is controlling here? Is this a kinetic control or a thermodynamic control? Kinetic! Yes, it's kinetic, because it's all to do with the transition state you're going through and not the stability of the product. And that's the Hofmann elimination, so keep an eye on it. You now have some useful ways of going about your business in terms of making alkenes. If you wanted less substituted, you could use potassium t-butoxide or the Hofmann elimination. And again, you can see now that this is useful for putting double bonds places that maybe they didn't want to go in the past. What is an even better way of doing this? What is an even better way of putting a double bond anywhere you want to without having to resort to this type of chemistry? What's the best way we've used of making double bonds this term? Wittig reaction, right? The Wittig reaction is even better and more versatile than this, but this happens and you need to be aware of it. So conditions down there, just to finish off, yes, it's some sort of amine, alkylate it, and then heat it with the silver, and away you go, you get the Hofmann outcome. It's the opposite of the Zaitsev. So I don't even remember, oh, I do remember what this stuff is. 2310 and 2311, just we don't have time. Yeah, it's a lot of old dye chemistry in terms of colorful materials and stuff like that. It's interesting, but I've got more interesting things to talk about, I hope. Make a note of that. We're not going to cover it. Now, to finish this off, nitrogen heterocycles, some of which we have done in the past. It tells me what these things are underneath here, so it's good. We've got some interesting compounds here with lots of nitrogen involved. The pharmaceutical industry relies upon nitrogen to form heterocyclic compounds. And some compounds that you will see an awful lot of in the future will be imidazole, which is based into things like histamine and things like proteins. You'll think now, basic, this guy here, this nitrogen is basic. This will be used as a weak base in biochem to deprotonate things. Simple ideas. Is this a Huckel system or not? Is it a 6-pi system or not? Yes, it is. You've got 2 electrons from each pi bond plus 2 electrons from the lone pair. That's a 6-pi system. So if I asked you which nitrogen was basic, which one would it be, left or right? The one on the right. The one on the right, the lone pair, is not part of the pi system. It's pointing outside, so it can be basic. Well, heterocycles are interesting. I'm going to mention this, and then I'm going to... Yeah, I'll get through this now. Look at this. Pyrrole is very much like benzene. And if you react benzene with bromine, Br2, it doesn't need a catalyst. Pyrrole does not need a catalyst, but benzene does. What does that tell you about pyrrole in terms of its nucleophilicity? It's more nucleophilic. What is this species here? Look at this. Nitrogen next to a double bond. What is that? Enamine. And what do you know about enamines from the past? They are nucleophilic. Yes, they are nucleophilic double bonds. So we can use this lone pair to help out and push these electrons around and make these positions more nucleophilic. And so this is much more nucleophilic than benzene. It does not need a catalyst. Follow that through. You can do brominations quite nicely and very high yield without having to worry about any catalyst. Look at the bottom. The question you should be ready for and thinking about is why does it go here next to nitrogen and why does it not go there? And the answer is quite simply resonance. If you alkylate or brominate at the position next to nitrogen, you get 3 resonance structures for the intermediate. If you put the bromine here, at the next carbon along, you only get 2 resonance structures. So more delocalization, the better. The pathway to go to the 2 position is lower energy, and that's why that goes there. Okay. Other examples of this, pyridine. Look at those conditions at the bottom. Look at the difference here. Pyrrole, 0 degrees C. Down here, 300 degrees C. What does that tell you about the reactivity of pyridine versus benzene? Yeah, it's not very reactive. Why not? Well, look at pyrrole. If you were to draw resonance structures for pyrrole, you'd put some delta negatives all over that cycle. If you draw those pictures for pyridine, you'd draw delta positives. That makes it less nucleophilic.